So right now I'm just going to start the recording, and it will be available. We'll have a link at the end that you'll see. Actually, it's at the beginning, so let's just start there. You can feel free to use this as the place to go to get the recording, which is going to be on the NCADE YouTube channel here. So as far as that goes, that'll be available in case we go over something that isn't 100% clear. Feel free to jump in with questions at any time. And also, you'll be able to obviously pause the recording later down the line if you're kind of going through everything on your own. And so if you also go to the NCADE website, there's a link to the YouTube channel there. So if this crazy acronym is a little bit tough to type in, let me actually just type that into the chat box, and that way you can paste it over on your end. There you go. Okay, so today we're doing part 2. Yesterday was part 1, and again that'll be, so I guess I should have changed this to, so this should actually be yesterday, and this is today, where we are now. And basically what we have is the technical steps today. So yesterday was more of an overview of all the different steps in conducting a multiple regression, and today we're going to sort of get into the nitty-gritty of how it all takes place within the SPSS environment. So just a quick recap, what we have is sorry, I'm getting an echo, so I'm just going to mute everyone, and if you want to ask a question, just use the raise hand button or type into the chat box, and I will do my best to answer your question when it comes up. It is a 2-part series, so if we tried to squeeze it into one, it would go way over the time limit. So this is just the facts of life, if you will. So the question that we're going to be examining is with a data set that you can download from this website here. And as a side note to that, the idea is, okay, if you missed yesterday's webinar, then it's going to be posted. I'm going to post both of them right after this one is done. So again, you can use that YouTube channel to view both when we're done. So that is sort of the best way to go about that. Now, what we have is a data set that has 4 variables in it: physical health symptoms, so the number of physical health symptoms, the number of mental health symptoms, and number of stressful life events, and also the number of visits to a health professional. So as I sort of briefly mentioned yesterday, these are all continuous, also called quantitative, also called ratio variables. SPSS actually calls this a scale variable. So when we, in a minute, look at the SPSS environment, we'll see all of those in a spreadsheet, if you will. And the idea here is that, we're trying to predict the number of visits to a health professional. That's going to be our outcome variable. And the other 3, the number of physical health symptoms, the number of mental health symptoms, and the number of stressful life events, we're going to use to predict visits to a health professional. And, the general idea is if you kind of imagine that this was your research project, you would be potentially interested in the way that these variables can be expected to help you understand what causes people or what is associated with people coming to visit a health professional. And in turn, the real sort of big picture question is that if someone visits with a health professional, maybe a therapist or a clinician, that could be related to obviously improving their overall well-being. And there's a question, is this a continuation of yesterday's work? This is not really a continuation. This is the same thing, except we're going to be looking at the technical aspects of the concepts that will be that were reviewed yesterday. So basically, it's the same thing, just we're going to look at the technical side of it. Okay, so as we looked at yesterday, there are a number of steps in the process. So first we have to enter the data. And once we've done that, then we can begin to do screening. And what screening does is it basically allows you to run through your data and figure out if there are any problems with the model. So we can take a look at that when we get there. For now, this is just a sort of overall outline. Then once we have all those diagnostic values from the first regression run, then we can start to address any violations of statistical assumptions, because we'll know what the model is actually doing under the hood. We'll be able to look at overly influential individual cases. And then once we have sort of ironed out all the problems with the data set, then we would run a second regression and again look at how well it's improved after we've administered these sort of tweaks, if you will. And then hopefully at that point be able to do a final analysis and make some conclusions about the data. So the first step is entering data into SPSS. So at this point, the videos are not posted yet. So once this talk is done, then we can you'll be able to view both. So instead of looking at it in PowerPoint like we did yesterday, let's actually look at SPSS. So the first thing that you get when you open it up is a data window, right? So the idea is you can either type in variables by hand, or you can open a data set that's been provided to you. Some people work with different organizations that have archival data sets, for example. What I'm going to do is just go to this open file folder here, and then just basically load up the data file that we're going to be using. This is the one that I downloaded from that website that I showed you on the previous screen. Let's see, presentations. Okay, and so there's my SAV file. Oh, it's on my second screen, sorry. There it is. And so now we have our data, and essentially you have your 4 variables as well as a subject number. That's the first column is the subject number, and then all the 4 variables that I just briefly discussed are here. So these are each person here is an individual case, right? So we've got subject number 4, and they have, they visited with a health professional 13 times, they have 2 mental health symptoms, 2 physical health symptoms, and they reported 241 stressful events. So if you go to the variable view, this is where you can create new variables if you like, and it's just kind of an overall summary without going into each individual case. So here we have the labels for the variables. This is also very useful, and sometimes for different variables it's useful to have value labels. So that doesn't pertain to us because we're using all continuous variables, right? These variables range from anywhere from 0 to, well, theoretically infinity. Mental health symptoms, physical health symptoms, and stressful events are the same thing. You notice that these numbers are not on a 1 to 5 scale. They're not yes or no questions. They're all what SPSS actually calls, if I go into variable view, SPSS actually calls these scale variables. So you have to tell SPSS what kind of variable you're entering if you ever are entering variables. If you have a variable that's nominal, for example, race or gender, that's a nominal variable. It doesn't have values that you could, manipulate in terms of dividing or multiplying or transforming because they're just labels. However, for our case, since we are using continuous variables, it would be all scale variables. So now that we have the data in SPSS, we can go back and look at the actual way to enter commands into SPSS. So yesterday I briefly mentioned this notion of whether we want to paste or not paste. So that's one of the main differences between running just sort of preliminary exploratory analyses and actual, consistent with a really methodologically sound way of conducting your data analysis. So as I mentioned, you can hit OK or use syntax and also annotate text. So we will look at that in the actual SPSS environment. So what I mean by all that is, let's say you want to do an analysis, right? And I mentioned the first step is to actually conduct a first run of the multiple regression, right? So you go to Analyze Regression Linear, and then here are those OK and paste buttons that I was talking about. But first, before we can do that, we need to tell SPSS what we want to analyze, right? So we're trying to predict the number of visits to a health professional. That's our dependent variable, right? Outcome variable, dependent variable, those are basically the same thing. I am not showing my screen. Oh, dear. You should be seeing it. Would someone confirm for me that I am? Okay, perfect. Thank you. Sorry about that. Okay, so let me actually do that over then. So what I said was, okay, we're going to go to Analyze, Regression, come on, Linear, and then our dependent variable, right? We're trying to predict the number of visits to health professional, and we're using these three independent or predictor variables. So mental health symptoms, physical health symptoms, and stressful life events, right? So again, the first step, like I mentioned, is to basically get these diagnostic variables that we need to kind of understand how the model is performing. So when you go to the statistics button here, it pops up this window, and you basically want everything, everything except that is this covariance matrix. We're not necessarily going to be using that. So essentially, you want all of these different statistics, and here you'll notice that you get case-wise diagnostics for outliers outside 3 standard deviations. Here you can either use 3 or 2. I'm just going to use 2.5 as a value, and we'll kind of see how that pans out later. But for now, this is what you need to kind of know. For plots, here, this is a very important piece of information, because this is where we get our residuals plot. And as I mentioned yesterday, everything is going to sort of revolve around how well the residuals plot looks, and this is an important measure of how the model is able to predict the number of health professional visits. So what we want is like, okay, what are all these weird, names of variables here? What we actually want is we want the z-pred value. This is the predicted, the value that is being predicted. So essentially, if you have from 0 to 100 doctor's visits, that's what's going on the x-axis. That's why we're putting this under x. And then the z-resid is the y-axis. So basically what this graph is going to be doing is it's going to be providing us with information on, for any value that's predicted, how far off of that predicted value is the model making a prediction. And we're also going to ask for the histogram, and that will also tell us, it's a different way of looking at the residuals plot. And so we're going to look at that as we go through. Now, as far as this third option, save, there are also a number of important variables that we want to get from SPSS and actually have, I showed you how there are 4 variables. We've got time, doctors, mental health, physical health, and stress, etc. This is going to generate some other values for us that we're also going to want to look at in terms of how well the model is performing. So we want to know about the predicted values, so save those. We want to know about residuals. Typically, you only want standardized residuals, but you can also look at unstandardized residuals. And I'm going to do both just to sort of show a couple of interesting ways to understand how these variables all interact. Influence statistics, this is very important. As we looked at yesterday, we want to look at standardized DF beta and standardized DF fit, which are measures of how each individual case, each individual participant would be influencing the model. We also want Mahalanobis distances, which is a measure of how big of an outlier each data point is. And then from here, we can say OK and continue. And then everything else is fine. So once you've hit those 3 boxes, the options, these values are the default values, and you can just leave these as is. And then bootstrapping is a technique that we're not going to be going into. It's a much more sort of in-depth way of checking the model, which is not really relevant to our needs here. One other interesting thing that you want to keep in the back of your mind is the method of entry. This is the way that variables are entered into the model. And basically what it pertains to is whether or not any variable is given priority over other variables. If we, for example, selected stepwise, it would put the variables in a different order, and it would have implications for how the variance or the variability of the visits to mental health professional variable is apportioned to different variables. The way that we're going to do it is just by entering them simultaneously, which is this enter command. But there are, of course, other ways that you could do it that are just sort of we're not going to have time to go into. So once you have everything sort of set up, then again the option is, do you hit OK or do you hit paste? And like I mentioned, it's better to hit paste. And what this is going to do is it's going to hang on, before I do that, I just need to make sure of one thing. Okay. So what I'm going to do is hit paste, and what you'll see is that it's going to open a new window, and this is that syntax file. So this is a whole bunch of gibberish, right? What are all these things saying? Essentially, you don't have to worry about that so much as you do about annotating the syntax. And what annotating syntax does is it allows you to sort of make notes to yourself about what that chunk of text is actually going to do. So what I'm going to do is, first of all, I need to type in an asterisk, so the number that's over the 8 key. And essentially what that does is it sort of grays out anything that you would type in until you press period. And you see how that kind of changes the highlighting on the text, right? So what I'm going to do is type in, okay, preliminary regression to obtaining diagnostics, right? Period, and then it activates, and then what I do is I place the cursor, I place the cursor at the beginning of the code here, the text, and then I hit play or run. And what SPSS does is it'll keep reading everything until it runs into a period, which is here, all the way at the end, right? So you place your cursor here. Dataset 1 is already activated, so I can just make sure of that by hitting play. And you see that all it did was run dataset activate 1, it hit a period, and that's it. So now I can place the cursor here at the beginning of regression, hit play, and see it's running regression down here. Okay, so now it basically gave us a regression model. And a lot of the time it's tempting to say, okay, so I put in my variables, everything is great, now just give me the output. I want to know what the data are telling me. And you could certainly do that, but it's it would be misleading to look at the output at this point. So what we actually want to do is first we want to get some descriptives. So basically, as we go, hang on, give me 1 second here. Just need to organize my other screen. So we first want to obtain the values that may or may not have been entered incorrectly. So before we sort of look at the diagnostics, we first want to look at descriptive statistics of our variables. So you go to that option of Analyze Descriptive Statistics, and essentially here you'll notice that now we have all of our new variables that it calculated. These are the diagnostic variables, but for now we only want to look at the 4 variables that are of interest to us. So we transfer them over to the variables box. You hit options, and here are the values that it can give you: the mean, the standard deviation, variance, range, minimum, maximum. These defaults are fine. We also want to know about skewness and kurtosis. This is for each individual variable's deviation from normality. So all of these values will be important in terms of figuring out whether or not any of our data are in fact skewed or in some way problematic. So I'm going to paste this in, and here, so notice I'm just kind of like going into the syntax in it, and it's kind of up to me to decide, okay, when am I going to run which piece of syntax, right? So I can just as easily run this descriptives command before or after running this regression command. So here I'm going to say, okay, so let's see, preliminary view of variables to identify out-of-range values. And the reasoning behind this command is that you basically are able to look at your data and make sure that all variables are in fact entered in a valid manner. So let's say that you have on your particular research project a Likert scale, right? And so that could mean that values from 1 to 5 are valid. But then it might turn out that, for example, either someone sent you a set of data that has a bunch of 6s in it, or you may have just, sneezed while entering a 5 and accidentally hit a 6. So this is a way to basically make sure that that's not the case. And this is very important because if you do leave those out-of-range values in, then essentially it makes it such that you're analyzing data that are not valid, right? So you want to make sure to do this. And so you hit play on that, and now we can look at the output. Let's make this full screen. And so here, you notice on the left, we've got this sort of tree structure, right? I had that regression earlier. I don't want that interfering with what I'm looking at right now, so I'm just going to hit that little minus button, and it collapses everything from the regression command, and all that I have now is just my descriptives. So we can see, okay, we've got our values. We've got 465 cases, and so we can look at each variable in turn and find out if there's anything that's all right. So, okay, it looks like visits to health professionals, we've got a minimum of -27, a maximum of 81. Right now, that should be a red flag, right? How can someone have less than 0 visits? That doesn't make sense. We can also look at the mean and the standard deviation and the skewness. The skewness tells us whether or not there's a bunch of values that are sort of towards the low end of the range and a few out to the large end, and a positive skewness statistic is indicative that there is, in fact, a large positive skew, meaning that there are a few people who have a lot of doctor's visits and a bunch who have only a few. So you'll notice that the maximum is 81, right? So it goes from, well, I'm sure it doesn't go from -27. We'll have to take a look at that one in a minute. But basically, it gives you an idea of the shape of the distribution. The kurtosis also, the larger this number, it means that there's a lot of values that are within a small range and then a few out on the tails. So, okay, we can look at the mental health symptoms. Looks like we have a minimum of 2 and a maximum of 15. That's interesting. We start to get an idea of our data, right? Important to know what our data actually look like. The standard deviation, that looks okay. We've got a mean of about 5 and a standard deviation of 2.4. So we know that it's a relatively stable distribution. It's also positively skewed, but less so than visits to health professionals, and so on. Now, the same thing holds for physical health symptoms. It's a relatively stable distribution. You see, it's not that skewed. It's not that flat or tall. And stressful life events, the last one ranges from 0, okay, that makes sense, to 9,200. Okay, that's a big number. The mean is 222, and the standard deviation is pretty big too. If we're dealing with such large numbers, that makes sense. But you'll notice here the skewness, it's 18.7. Okay, even with a largely skewed variable like visits to health professionals, only 3. So this has a huge skew. So I'm wondering if this 9,200 number is what's causing that. And so we can certainly look into it. The way that you would look into it is you would go to Analyze, Descriptives, and then it might actually be under Descriptives. Nope, sorry. SPSS has a few of these different descriptive commands. So we would, I think, go into Explore. And yes, and we already have descriptive, so we don't want these. We want outliers. So what this will tell us is the highest and lowest values, which is important because, remember, we saw that there's a -27 here, And that seems to be a problem. And then there's this 9200 value. So we kind of want to look at the outliers and see, okay, what the heck is going on here? And of course, we have to tell it which variables we want to look at. So we want to look at all 4 again. And you can also obtain plots. Typically, I'll just look at a histogram of each variable. And this is just another way of obtaining the same information that's in this table, just in a visual way, if some people are more inclined to look at it that way. So we paste that in. Go back into the syntax. And this is basically the same piece of information as here. So I'm just going to copy this and paste it in here as well. Okay? But now I'm just going to say with outliers and graphs. Okay? And so now when I come back to this later, after forgetting all about it for a day or two because I have exams, then I'll know exactly what I was doing. So then I hit play on this. Oh, and by the way, you can either select all the text you want it to run. So for example, I could just run all of this at the same time if I select all of it. But for now, I'm only interested in running the exam command. So you see this little arrow thing. It says if I click the cursor here, it's going to run everything from here until it hits a period down here. So this blue bar will tell us what it's going to run when we click in a certain place in the syntax. So I hit play on that. Now it's running exam, and it's thinking, it's thinking, it's thinking. Boom, there it goes. So again, I already have the descriptives up here, so I can minimize that. And now, again, it's telling me it processed 465 cases, and here are our extreme values. Okay, so we can see that visits to health professionals, these are the highest 5 and the lowest 5, okay? And you've got the case number, so if you were to go into your data file, you could identify them, and you see 81, 75, 60, 58, okay. The 5 lowest, of course, there's a bunch of zeros. That makes perfect sense. This negative 27, that's the problem. If you were to run the analysis with this value in here, it wouldn't make any sense. That value needs to go. There's something wrong with it. You know which case number it is. So you would literally just go into your data file, and now we're in variable view. And so hopefully at this point, you're starting to see that all these diagnostic variables, we don't really want to know what they are because we've got a data point that is skewing the data set. So we go into data view, and we're looking for case 102. Okay, here's case 102. And yes, there is that funky variable. So essentially what you would have to know is, okay, what could be causing this to be negative 27? If you go into, like, if you coded these by hand, you can go back into your data and see, oh, okay, that's just an error. Maybe I meant to type in 27. And in this data set, that actually is the case. So, you know, admittedly, I just put this in here, but it's just as an example, right? So you change that. Okay, that's good. And then if there were any other kinds of problems along the same way, you would want to address those too. Okay, so we go back into our output. And now, remember, there was that question of what's up with that 9200 variable, right? For mental health symptoms, the highest values are, you know, they all look to be in order. Everything, there's no huge leap from one to the next, right? 15 and 14, and then the lowest ones are 2s. For physical health symptoms, we've got, you know, everything looking okay. But then here for stressful life events, you see that the highest value goes from 9200 to 731. And then all of these are in the, you know, sort of 7 to 500 range. And then you've got something that's an order of magnitude larger. So there's a question, why wouldn't we exclude case 102? The reason that I didn't exclude case 102 is because I sort of am doing a bit of a mental leap. I would look back in the data and see if I had my spreadsheet in front of me, and, you know, if I was coding everything by hand. You know, I interviewed all the people and I found out the number of doctor's visits, and then I went back in my records and saw that I just entered that value incorrectly. So it was meant to be a 27, but I accidentally entered it as negative 27. So that could be one way to figure out why that value is wrong. If you can't find a reason for it to be wrong, then yes, it might be the case that you should exclude it because it just is an anomaly. So sometimes you would exclude the value, but other times it is you're able to find out what the reason was, and you can just input the correct value, basically. Okay, so for stressful life events, I gotta wonder, is that 9200 really supposed to be 9200? So again, just as I did with the other one, I would go back in and say, okay, what value is that supposed to be? And, you know, given what I know about, you know, my data set that I entered by hand, I know that it was supposed to be 920. And so, okay, I guess that I just made a typing error when I did that. So these are, of course, extreme examples. But again, for your own data, especially when you're dealing with continuous variables that you know the range of and it's more limited, then you can start to make more sense of them. Okay, so I'm going to go back in, and I know that it's case 4103, right? So I go to my data, go to case 403, and address the problem. Okay, 9200. Okay, that was supposed to be 920. Good job, Kuba. Okay, 920. Good. So now I've done this sort of out of range analysis, and now I want to save the data file, right? Of course. But see, what's interesting now is we've got all these diagnostic variables, right? And notice that 9200 value, it's 21.9. It's a lot bigger than all these other values. So I'm no longer interested in these diagnostic variables. Okay, so I right-click on them, clear them out, no longer interesting. It's not a big loss. But now that we've done this sort of out-of-range analysis, we want to go back in and actually obtain the diagnostic values that are of interest to us. So what I want to do is I could just go into, analyze, regression, linear, and then just here rerun the same exact analysis, right? All the values are saved. Everything is saved the way that I had it a minute ago. But if I had to close SPSS, all this will be cleared out. So again, I'm not going to do that. I'm not going to do that. I'm going to go back into my syntax, and I know exactly what I did. I have the same exact variables that I'm analyzing, so I'm just going to rerun the same piece of information, right? And again, so the regression command goes all the way down to here. I hit play, and now these are going to be the diagnostic variables that I actually want to look at, okay? So, we've done our out-of-range analysis, so that's good. Now what we can do is look at the residuals graph. That's the first piece of information we want to look at. And then we want to look at the heteroscedasticity, the multicollinearity, which are model-related variables, which have to do with the way that the variables and the model sort of interact. And then we also have multivariate outliers and influential cases, which are specific to each individual participant. And so if there are no violations, if the model is performing perfectly well, then you can actually trust the output. But, spoiler alert, there are always going to be violations, so you always have to check these, and inevitably there are going to be some issues that have to be resolved. So what we do is we look at the residuals first. Remember I mentioned that residuals are important. This is just a recap of yesterday. The residual is the difference between the value a model predicts and the value that's actually observed. So large residuals, so each observation has a residual, right? The difference between what the actual observation is and what the model predicts that value to be. And so the difference between those is what we're really interested in, and that's what a residual is. So large residuals are a hint that the model is unable to predict observations well, and as I mentioned, it's kind of like a canary in the coal mine. So what we do is we go into SPSS and we say, okay, SPSS, tell me what I need to know. So we go in, and so this is variable view. We want to actually look at the values that are important to us. So we want to look in the output first and look at the residuals graph. So you'll see that, okay, first of all, I'm going to minimize all the stuff that we did before, right? That's no longer relevant to the step that we're at. And so all I have, right, everything is, there's no confusing which output I'm looking at, right? Everything is just, it's just syntax that it pastes in. And now here is the regression output that we want to look at, okay? The very first thing I want to see is what the residuals plot looks like. And so here, you see that for a number of cases, it's a difference of 0, right? The actual values that the participants report in terms of the number of doctor's visits and what the model predicts is pretty good. The difference is 0. So you have a bunch of those, and that's really good. The problem is that we have a whole bunch of stuff that's all the way out here, right? And these are standardized, meaning that we're not looking at raw values here. We're not looking at the difference between, let's say, if somebody reports 50 and the model predicts 100. We're looking at the number of standard deviations away that that an observation falls versus what the model predicts. So a value of 8 is huge. 8 standard deviations is like you would expect 0.00000001% of your data to be that far away from the mean. And so we can also look at the scatter plot. And so here, we're looking at a bunch of values that are close to 0. So that's good, right? Regardless of whether it's few doctor's visits, which is towards the negative side of the predicted values, or whether it's a high value, there are a number of predictions that are pretty good. There are not that many standard deviations away from the mean. However, once we start going above 2 standard deviations, that's where we have to worry. So everything up here is problematic. And it means that the model is unable to predict a really big proportion of values in a manner that's really accurate. So that's a problem. And essentially, once we have that information in hand, we have to start addressing this problem. So that's what we're going to do next. We're going to see how we can sort of address this. And basically, if we just hop back into PowerPoint for a second, just a quick summary of what's happening. There is an issue with the number of residuals that are poorly predicted. Right? We've got 21 cases, or about 5%, with large residuals. We also have a bunch of positive residuals, but constricted negative residuals. And then the question becomes, okay, so what's causing this poor prediction? We have those 4 options, right? So next up, what we have to look at is the possible causes. So heteroscedasticity is basically what we've looked at in this graph. I went over this yesterday, so I don't want to go into too much detail, but basically you'll notice that we have a combination of problems. We have a bunch of values that are really close to the mean and then a bunch that are far away from the mean, right? We looked at the negative values that are all kind of scrunched up and the positive values that are all spread out. And we've also got a bit of a funneling problem. So at high values, we have a bigger spread of residuals, but at low values, we've got a small spread. So the problem with this is that what the model could be doing is it could try to make estimates, right? And it tries to draw a line of best fit that it could look like this and still be accurate. It could look like this and still be accurate, right? Or it could be flat and it could still be accurate. So no matter what the model decides, we can be pretty sure that it's not going to be accurate. So when we look at the output, there's a way that you can tell that that's actually happening. When you look at the output, obviously, okay, so here's that problem, right? We've got a bunch of scrunched up values, and we also have this sort of funnel shape. The higher the number of doctor's visits, the less able the model is to make good predictions. Okay, and we can tell that by looking at the actual output from the model. Okay, and what we can look at here is the width of the confidence interval. Okay, and depending on how wide this interval is, it will tell you that for each predictor, whether it's mental health, physical health, or stressful events, we have coefficients that we use to predict the strength of the association between the 2 variables, whether it's mental health and number of doctor visits, physical health and doctor visits, or stressful events and doctor visits. And this is the spread of that estimate. So actually, when you're looking at the unstandardized values, you see that for mental health it's 1.8, but it could be as low as 1.3 and as high as 2.2. So we want to get that confidence interval down, and that's what the residuals plot is sort of the canary in the coal mine of, is how good is our model at predicting it. If the spread is really big, that's no good, especially if it crosses 0. If it crosses 0, then it means that we want to be sure whether it is crossing 0 or not. Anyway, okay, so moving on, what we have to do is address this question. And one of the main ways to do that, excuse me, if we know that the variables are, if we know that the residuals are sort of positively skewed like this, one of the main culprits of this is variables that are not normally distributed. And remember, we looked at the at the statistics for the for each individual variable, and we saw that a bunch of them had positive skew, right? So that's one of the typical causes of this kind of problem with the residual graph, which could be a cause of the model being unable to predict doctor visits with a relative degree of accuracy. So essentially, what we can do is we can look at how skewed these variables are. And we had this in the explore command, right? So we have visits to doctors. No surprise there. Okay, so we know this still had that negative 27 value in here, so we can ignore that. But still, we have all of these positive outliers, right? So that's a problem. The box plot is the same way of looking at this, a different way of looking at the same information. For mental health symptoms, okay, we see that there is still some positive skew. One way to look at this is if you double-click a graph. Oh, of course, it's showing up on my other screen. If you have a distribution, you can click on it, and then there's this cool little button that will overlay a normal distribution on it. And so you can see that there's nothing on the left end for our actual data, but there's a lot of positive outliers. So, okay, that could be a problem as well. And we can do the same thing for physical health symptoms. This one is, still some positive skew. So, okay, that might be an issue. Boxplot tells us the same thing. Now, obviously, with stressful life events, we still have that 9200 value in here. So I can just very quickly get a quick graph of just stressful life events. I'm going to take all these 3 ones out of here. I know that I'm going to get my histogram, right? I don't want any statistics, so I'm just going to click down here and say plots. And then, okay, I could paste this, but this is just a quick check, so I don't even care. I just want to look at it very quickly and see what it looks like, right? And there's my histogram. Okay, again, looks pretty positively skewed. In fact, that 920 value is looking like it's skewing everything. So what can we do about this? Well, the notion is that if you have these positively skewed variables, we know from just, decades and so forth of publishing research and looking at what is going on with potential problems with regression models that non-normally distributed variables could be the culprit. So what we want to do is we want to transform the variables. But before we do that, I am going to sort of focus on that because we will run out of time relatively shortly. But what we should do as a check, I don't want to downplay the importance of this, is remember I asked for all of these variables, right? So we want to look at the Mahalanobis distance. We want to look at the DF fit and the DF betas for all the variables. And what these variables actually tell us is what I want to just very quickly review. We'll look at them, and then we'll do the transformation and look at how that impacts the ability of the model to predict the values. So I just have to get PowerPoint up and running again. So what we want to look at are these issues of the observation-based, where's the button? Hello? Ay, ay, ay. Okay. Come on. Okay. Are these observation-related variables that we're going to look at really quickly? So basically, we've got the Mahalanobis distance, right? This is the measure of the distance. This is a measure of the distance of a case from the means of the predictor variables. So how far away from the overall center of the line of best fit that the regression model generates is each individual person's data. And so yesterday we looked at the critical value that we would need. So we know that it's 16.266. You can see that here. And so what we do is we basically look at our data, and we can sort the data by the Mahalanobis distance. And then we're going to create a new variable, we'll call it run2, and code the cases with that variable. The reason that we're going to do that is because we can then filter out those data points that are causing these problems. So, okay, I'm going to go into data view, and then I'm going to take my data and sort it. And it asks me, okay, what do you want to sort it by? And then I say Mahalanobis distance. And I want to do it descending so that I have the highest values at the top. And then I'm going to paste this in, and this is just so I remember later that I did this, right? So I will have to annotate my my syntax and say, okay, that's a pretty straightforward command, right? I don't need to annotate that because I can just sort of read that in plain English and understand that that's what it's doing. So I hit play, and then it didn't do anything to the actual output. What it did do is sort the actual data file. So we go in here, and then we go over to Mahalanobis distance. Oh, it's right here. Okay, so that's the variable we want to look at. And all the way at the top, okay, we see that we have 3 cases that are higher than that critical value that would qualify a data point as an outlier. Okay, so now I want to flag these guys, right? So I go over here all the way to the right, and I just make a new variable, and I just put in a couple of ones that I know are going to be problematic. So now I have a new variable here, and then I can rename it under variable view. And this is just, I'm calling this run2, right? Well, run2. And then later, what we also want to do is sort the data not only by the Mahalanobis distance, but by these other types of variables. So if we look at, okay, let's minimize this. Okay, so that was the Mahalanobis distance. So we know that we have 3 cases that are problematic, right? Yields 3 cases. And then now we want to look at the influence of an individual case. So this, remember, we looked at, well, for some of you, remember we looked at this yesterday, and this is a correlation between murder rate and violent crime rate, just an example. So we have 50 states, and there's a pretty good positive correlation. You can see that line. And what could happen is if you had, so this last data point that I'm adding in here is the data for DC, Washington, D.C. And so it could be that it's an outlier, right? Wonderful. But you see that the line doesn't really change much. However, if we had an influential outlier, if there's a different relationship, then you can see that it's changing the value. So if it's an outlier like this from the rest of the data points, no big deal. But if it's like this, now you can see that it's making a big change in terms of how the model fits. So what the DF fit statistic tells us is how much of an outlier is the case. So the idea is if we had this data, right, and then we have that one data point that, come on, I want the marker, and it's not cooperating right now. And we have the data point here, then, it's saying this is the distance from the line of best fit to that data point. That's what DF fit tells us. The other piece of information is DF beta, which is basically saying how much would the line change if you include the outlier. So it's basically saying, okay, going from that to this, right? The line changes, and what's the extent of the change of that line of best fit. So that's what these 2 pieces of information are telling us. And basically we want to look at the standardized forms because if you're looking at each individual variable, then you have to know the scale of each variable. So we know that one variable goes from 0 to 920, right? So a change in the non-standardized DF beta would have to be a lot larger than the change from a variable that goes from like 0 to 20, right? And so you'd have to do all kinds of mental arithmetic, and it's just easier to look at the standardized versions because there we know that values between -1 and +1 are okay, and everything outside of that is not. So then we look at those pieces of information, right? And we have these values ready to go. We just have to sort the file by those values, okay? And so, again, you can sort them by standardized DF fit, again, descending. In this case, it doesn't matter. I'm just going to hit OK for the sake of time, but always remember to do it in terms of pasting. So, okay, we know that this one value is greater than 1. Okay, so we want to flag that data point. Aha, notice this is the same offending variable, right? So now we know that this is something that we need to watch out for. Of course, we have to look on the other end of the distribution because there could be values that are also smaller than 1. And notice these values, they're not less than -1, right, on the DF fit variable. But they do have large Mahalanobis distances, so they are outliers. So we don't necessarily have to worry about these two. But in any case, it might behoove you to run the regression with and without them. Anyway, we would do the same thing for the SD betas. Right now, for the sake of time, I'm going to skip over that. And anyway, if you only have 2 or 3 data points that are influential, it might not even be that big of a deal. However, I don't want to downplay the importance of it. You would want to rerun the analysis excluding the values that you identify. So at the very least, you'd want to rerun the regression and see whether or not anything changes. What I want to do, though, is, again, I mentioned that one of the main underlying reasons for a really messy residuals plot is that variables are not normally distributed, and that is, in fact, the case for the variables that we looked at, right? We looked at those histograms, and we saw that there's a bunch of data out on the right-hand side of the graph. So what we really want to do is conduct what are called transformations. So basically, what we want to do is, well, yeah, so this is just looking at individual variables, and we basically look at transforming variables. So for positively skewed variables, which is the case for our data, we have 2 standard types of transformations that we can do for positively skewed variables, and one is a log 10 transformation, which you have to add 1 because the log transformation, if you have a minimum value of 0, you can't take the log of that. I don't have the time to go into what that actually has implications for in terms of mathematics, but you can be relatively certain that if you have a minimum of 0 in your data variable, you have to add 1 to it, to all the data points, right? Just kind of shift it over by 1, the entire distribution over by 1, and then transform. So that's what we have. And the way that you would do that in SPSS, anytime you want to transform a variable, is, see there's a command for transform, and you can go to compute variable. So it asks you for a target variable, and I just typically would call this log and then underscore. You can't have spaces when you're naming variables. And so the first one we want to transform is our visit to healthcare professionals. That's our outcome variable. We know that's positively skewed. So log time DRS, okay? And then, sorry, I shouldn't have clicked that. So now what we need to do is tell, okay, so what operation do you want to do upon this variable? It's under arithmetic. Now there's, I don't know how you would know this, but you know, any stats book would basically have this information. And it's, see this LG10? So you go to arithmetic, LG10, and then it tells you, okay, returns the base 10 logarithm of the numerical expression, which must be numeric and greater than 0, right? So we know that it has to be greater than 0, so we go to log 10, and then it says, okay, what variable do you want to transform? So we say visit to health professionals, but we know that we have to add 1 to it. So we just say, okay, give me the log 10 of time doctors plus 1. Simple enough. And then we can paste that in. Now, here's another added value of the paste command, is that when you're in the syntax and you're computing a variable, you can simply copy this and then paste it and simply change the name of the variable here. So now I've got my time DRS, my other variables are called, right? I've got these 4 that I want to transform, right? So I simply go in here, I want the log of mental health, so I just replace that. I want the log of physical health, and I want the log of stress. Okay, and so now I can run this command, and essentially what I want to do is verify that everything worked, right? So what I actually want to take a look at is, again, those histograms of these new variables, right? So just to make sure that they are now looking like they're more normal. So I take my 4 variables, I pop them in here, I have my plot, histogram, and essentially I can now continue, paste that in, and now I should have, variables that approximate normality a little bit better. So it's running examine, it's ready, and so now we have, okay, so I can minimize everything else. Don't want to see that anymore. All I want to see is my histograms. Okay, so still a bit of positive skew for the number of doctor's visits, but it looks better. The mental health variable, also still a bit of positive skew, but it looks better. Now the physical health is definitely more normally distributed. And in fact, now what we have is with the stress variable, it looks like it's become negatively skewed. So we've got this variable in here, which has this value of 0. So in the end, you might want to exclude this, this couple of data points. But what you'd really want to know is, do I really need to transform this variable? The answer is no. It's not always necessary to have normality of each individual variable for multiple regression. The only thing that needs to be normal is the residuals plot, right? So in fact, stress, we can just leave stress as is. We don't necessarily need to use the transform stress variable. So in the end, what I can do is rerun the regression and take a look at how it's performing after I've transformed these variables. So remember, we have syntax for this already. So instead of going back in, I want to run the exact same regression as I did last time, right? So I just paste that in at the bottom here, except now I just change these variables, right? So I have all these log transformed ones that I had, except for stress. I'm not going to change stress. Okay, so now we have all these log transformed variables. We rerun the regression and have a look at the residuals plot. Okay, and so now you can see, remember last time the scale was going up to 8, right? And it was having trouble predicting the values that were at the upper end of the distribution. Now they're much closer to 0. And it's still a little bit funky, but it's much better now, right? So now what we would do is, obviously this is a sort of rough approach and we're running out of time, but I do want to make a note of the output that you get. So essentially, when you're looking at the model, you want to take a look at the amount of variance that you're accounting for. So that's the model summary. And what I'll do is I'll actually open up the the second one we did, the second one being the one that didn't have that -27 and the 9200, and we can sort of compare them side by side, right? So in the first model, we saw in the model summary that we were accounting for 21.4% of the variance in a number of doctor's visits. So that's okay. It's not a lot. And now, once we've taken the transformed variables, and if also we removed the outliers, it would be even better a little bit. Now we're accounting for 37.6% of the variance. So that's a jump of almost double. Now, what's also interesting is in the original model, if you look at the coefficients, previously we had mental health symptoms. Here's the way to look at this output: is you want to look at the unstandardized beta coefficient and the standardized beta coefficient. What an unstandardized beta coefficient is, it's saying for every 1 unit increase in mental health symptoms, how many units increase can you expect in the outcome variable, meaning number of doctor's visits? So here it was 1.78. Okay, so that's a pretty big jump. In our corrected model, it jumps down to 1.3. So that's informative, but remember, this is a log transformed variable, so that's a little bit funky. What you want to really look at is a standardized coefficients. And these tell us for every one standard deviation unit increase in the predictor, what number of standard deviation units in the outcome can we expect. So this is really the more informative value to be comparing the two models, any two models really, because now they're going to be on the same exact scale, the standardized scale. So it's 0.515 in the corrected model, right? And in the original model, it was actually 0.390. So we're actually seeing a stronger effect of mental health symptoms in the corrected model. For physical health symptoms, it was nothing. Negative 0.004. That's a tiny, tiny change, right? And the significance value was also nowhere near significance. Now under coefficients, we see that it's still not a very strong effect, but it's changed, and the significance value has gone down. This is still nowhere near significance, but you can see that it's changed. And for stressful life events, now we have a 0.185 beta coefficient. Earlier, it was 0.169. So not a big change, but still, we know that this model is better able to predict things, so we can trust it more. And also, the other thing, remember I mentioned earlier that we want to look at the confidence intervals, right? So if we look at the confidence intervals for mental health symptoms, the possible coefficient was from 1.787 to 1.353 to 2.221. And what we want to sort of look at is apples to apples, not apples to oranges. So unfortunately, we can't directly compare a 95% confidence interval to a standardized beta coefficient, but there is a way that you can transform the confidence intervals so that they reflect the standardized beta coefficient. We don't have time to go into that right now, but when you're running a multiple regression and you want to know how much it's improving, you want to look at the change in that confidence interval. So for example, we didn't transform stress earlier, right? Which means that in this model, in the original model and the new updated model, this is going to be the same. So we can compare the confidence interval for the stressful life events, and you can see that it goes from 0.007 to 0.021. What we're looking for is for this confidence interval to become narrower. And in fact, it is much narrower. So we know that the predictive value is improving. So that it's not that it could be as high as 0.071 or as low as 0.021. We know that it's really, really narrowly defined as being between 0.000 and 0.001, which is a much, much tighter confidence interval, which again indicates that that coefficient can't vary as much. It can only vary in a very, very minute way. Okay, so this is sort of the way that you would go about comparing how much your model is improving. And I realize that we're out of time, but I do still want to take any questions that you guys might have. So I'm going to unmute everyone, and let's see if there's anything I can sort of clarify. Oh, and I'm going to start with issues of multicollinearity and influential statistics. So remember I mentioned that once we find out that there is or there are a few data points that are problematic for us, then we can code them, right? So we did that for the Mahalanobis distance. What we didn't do is look at them in terms of the DF beta coefficients, right? So what I'm going to do is I'm just going to sort the data by each of these one at a time and see if there are any values that are outside that range, and then we'll take a look at how well the model reacts to any changes in that particular variable. Oh wait, no, we don't need the data for the intercept. Oh right, okay, so this is, yeah, right. Remember we added values, it automatically adds values from the log transform variable. So before we even get to that step, we would have wanted to look at the DF betas. So for the untransformed mental health variable, we can sort that. And these are, do these look sorted to you? They do not. Well, that's weird. Okay. Let me just sort them. Let me do something to see what the heck is going on here. Let's sort it by subject number. Okay, that's fine. Sort cases by not subject number. I want the SD beta for mental health. Okay. Oh, because I'm looking at the wrong variable. Haha, it's this one. Okay. So not a lot of issues with the negative side of the distribution.
You've never seen one of these devices before. It's kind of
Here's on the positive end, though. You see that there's a value that approaches 1. So I would want to flag this. So I'm going to just say I'm going to code this new variable as a 2, because remember, the code of 1, I can filter it by any value I want. So I could eliminate values that have high Mahalanobis distances, which would be a 1, or I can eliminate values that are high on any other variable that that I could be interested in. And in fact, what I'm going to do is I'm going to get rid of these variables, because these are the ones that that were on the basis of the second model. So we're not there yet. Remember, I'm kind of going back in time and looking at these variables that we skipped over. So at this point, what we have is right. So we look at this SD beta 1. We want to sort cases by this variable. And of course, I could be pasting this and changing it, but it's a simple enough command where I'm just going to do it manually. Okay, so this one, negative 0.42, not so bad. And all the way at the other end, 0.48, getting closer to 1, but still nothing too extreme. So I'll leave those data points alone. What's nice about this data set is that there were a lot of data. So 260 cases, that's a pretty healthy sample size. So we could be more sort of strict about what values we want to eliminate. So if you see a value that's even halfway to 1, that could be that's half a standard deviation of a change. So that's a pretty decent number to be concerned about. And if you're wondering, then of course you can look at the Mahalanobis distance as well and say, okay, if it's approaching 1 on the SD beta variable, how big is it in terms of an outlier all on its own? So remember, it can be an outlier. It's not necessarily influential. It can be influential and be an outlier. So in this case, the Mahalanobis distance is pretty small, and this isn't really approaching 1, so I'm going to leave it alone. And then finally, we have our other variable, which is stress. So we'll sort that by its df beta. And okay. So we see that this guy was already problematic. So I'm going to change this to a 2, because not only is it an outlier, it's also influential. So definitely that has to be excluded. How are we doing on the other side of the distribution? No, the highest value is at a negative 3.7. Now notice what's interesting here is that this data point was an outlier, but it's not influential. So if you exclude it from the equation, it's not that it's really skewing everything. It just so happens to be really far out on the scale. So that's basically synonymous with if we think back to our example, having this type of situation where yes, it's an outlier, but it's not really changing anything if it were missing, right? So the line looks like this if it's not there, and it looks like this if it is there. okay, maybe we want to leave it in, but sometimes to be on the safe side, you might want to exclude it. And of course, you could run the regression as many times as you want. We have the computing power to just kind of, run it over and over again. This isn't 1960 where you have limited computer time. So essentially, it's up to you whether you'd want to do that. I'm just going to exclude it for fun. And now what we can do is we have a few of these cases, right, that we've coded as a 1 or a 2, what have you. So we can exclude these, we can filter these out wherever they are. There they are, right? And just analyze the data without them. So the way that you would do that is you go to Data and select Cases. Now down here, you have a bunch of different options. So basically, you can say if condition is satisfied, and essentially, no, okay, that's why. What you first have to do is SPSS won't know what to do with blank values. So you first have to tell it, okay, if it's blank, just call it a 0. So first off, what we have to do is say transform recode into same variable, and we have our run2 variable, and then you just say, okay, old and new values. So what you want is to say system missing. This is everything that's blank. So for system missing, you want to just say 0. You add that in here, and that's fine. And then all other values, we want to say, well, no, you can just say leave them as is. So if it's a 1, it becomes a 1, no big deal. If it's a 2, it becomes a 2. So the only thing you're changing is that if it's missing, it turns into a 0. So you continue. And here, I'm not going to paste this because I'm just creating a new variable, so I may or may not remember what that is. In my case, I would remember, so I just hit OK. And now everything stays the same, right? We've got our 2's and just that we've added 0's into this variable. And now we can filter the data and rerun the regression. So essentially, right, we go back into data, select cases, and then if condition is satisfied, this is we want to exclude all the 1's and 2's, right? So we want to say if run2 is less than 1. So it keeps everything that's less than 1. We continue, and this, again, you can hit OK or you can hit paste. I'm a bigger fan of hitting paste on this just because later you can add a little trick of using all. And what use all means is, well, I'll show you. What use all does is, see how now these are crossed off? So whenever you run any kind of analysis on this data set, it will exclude all the values that are 1 or 2. You always want to double check to make sure that it ran it right. But yeah, so there's a 2, that's excluded. I think we had a 1 in here somewhere. Okay, there it is. Yeah, and it is excluded. Okay, so good. So now we know that it's being excluded. And the issue is that you always want to make sure that you're running the data on the correct data set. So if you have the filter command in there, then it's kind of a reminder saying, oh, right, okay, is the data set filtered? I want to make sure that that I'm not screwing this up and not analyzing all the data that I want to analyze, or in fact analyzing data that I don't want to be in the data set. So filter by df beta, df fit, and Mahalanobis. Okay. And now we have our regression command. So we would just run this. And now you can confirm that your data set has 461 cases. Right? Before we had 465, we've excluded 4, and we can, again, we can do a comparison. How does our model fare compared to before we excluded any of these data points, right? So we have that output up here. We can look at the coefficients again and see what effect doing that had. And if we're improving the model but only losing 4 cases, that's great. So here we can see that there is a bit of a change. Essentially what I want to look at is the change in the confidence interval, right? And I also want to look at a change in the residuals plot. So let's look at the residuals plot first. That's a more intuitive way. You know, it's a little bit improved earlier and now. Not that great of an improvement, right? So maybe we're not gaining that much from removing those cases. Certainly, it seems that we could focus in on the cases that are maximal. This is a little trick that SPSS has. If you double click on this, where is it? There it is. This window pops up called Chart Editor, and what you can do is you can identify these offending cases. So, whoops, I can right-click a data point and say go to case, and it takes me to the case that has this large residual, right? So notice you can look at the predicted value, right? This is the value that SPSS predicted for this case, which is 15.58364. The actual value was 75. Right? So the residual is simply the difference between them, like I mentioned. And you can, of course, look at the standardized residual value, and that's that 6.12 that we saw on the graph. You can also do a graph of residuals that uses, you can do a scatter plot of whatever you want, right? You can, for example, do a pre-1 versus res1. And so I'm not going to do that. Well, why not? Okay, so you can go to scatter plot, do a simple scatter, and just look at the raw values. If that helps you sort of think about it, it's going to be the same exact graph, except it's just going to have the y and x axes of the on the scales that the variables were actually measured in. So we've got the unstandardized predicted value and the unstandardized residual value. I'm just going to hit OK. And now you see it's the same exact. Oh, where is it? You can see it's the same exact graph. Well, I mean, it's scrunched up a little bit, but it's the same exact graph, but now we just see that if the value is whatever it was, like 15 point something, it's predicting a value of 60, right? So we know that it's not doing well at predicting that. So if this is a more intuitive way of looking at it, remember that when we did the initial regression, we saved both the unstandardized and the standardized predicted value. So now we're just looking at the unstandardized and the unstandardized residual. But anyway, the point being that removing those cases didn't really improve the residuals plot. So we would know that we have to go back in and remove the not remove, but transform the variables most likely. So that's just another way to kind of rerun the regression, check whether removing those offending cases fixes anything. In a lot of cases, it does. In a lot of cases, you'll have just 1 or 2 cases that are really wonky, and in that case, removing them will significantly improve the model. However, in this case, we knew that there was a lot of different problems, so it didn't really matter if we removed a couple of cases. And this becomes a much bigger decision if you have a smaller data set. So if you have less cases, you have to try to weigh the benefit of removing a case versus the benefit of the degree of improvement in the model. So there you have it. And I think at this point, I've taken up plenty of your time. In any case, let us know if you want any assistance with your data analysis. That's what we're here for. And